Hello everyone, good afternoon. Welcome to the class ECE341, the probability and the random process class. Today we keep working on the probability, right? Last time we studied what is a probability. We learned something about the sample space event, and then we define what is a probability. Okay. ECE341. This is the Friday's class, the first week, Friday's class. Okay, now we consider experiment, random experiment. With sample space S, and we consider event. We say A. A is the event of the experiment. In other words, A is a subset of the sample space S, right? The event A. Now, what is the probability? Probability of this A. How to determine this A? We need to repeat the experiment a lot of time, a large number of times. Then check how many times we get A. So here we repeat the experiment like m times. Then the probability of A will be the number of A happen. Right. A happens. So how many times A happens out of this M experiment? So we have this. Of course, here is a approximate. And when they are equal, that means M go to infinite. Right. When M go to infinite, they are exactly same. But of course, you can only have finite times. You can choose some large M. Then these two sides, they will be very close. Okay, now let's use I use MATLAB to do the experiment, do some experiment. Okay. Yeah. If you want, you can try. For example, you use a dice, or use a coin, or use whatever something. You just try to perform it, repeat it time and time again, and take account how many, like some event happen, and then give the probability. But usually that costs a lot of time, right? However, we have computer can run faster, so we can use computer to find the some, we can do some experiment and find the probability. Here we need to go to 341. Okay, 341. I have a folder. LS means list of the folders in this. I have a code. Which one is code? First one is code, CD code. Okay, some old code. Now let me edit a new file, which is a lecture for the 01, the first week, Friday.m. Okay. Now this command give a new file. Name is Lec01F.m. Okay, the file is here. I want to show some random values, and in MATLAB it contains the built-in function ran. Here. Ran. This ran give us its name is uniformly distributed random numbers. It will give like a random n is an n by n matrix with random entries. Choose from uniform distribution. We will learn later what is a uniform distribution. The value were in the interval from 0 to 1, 0.0 to 1.0. Okay, so this is random n. And here random n. This gives us a matrix with m by n matrix with random entries. Okay, now we just use this rand function to find some random value. We use this rand as an experiment. Okay, letter A. Use x. Okay, x is a value of some random value. How many random value do we want? We want like m equal to 1000. What happened? M to 1 and m. So this gives us 1000 numbers coming from this function random. I get x. Then what is x after we run it? Okay, sorry, too much. We try start from 10. Okay, then we can see what will happen. Then F5 will run this file. F5. It works. Oh, I need to save it. I need to save these in the just the save. Is it wrong? Try again. Oh, nothing happened. Yeah, I can see, but it actually happened here. I see. After I run, I have m and I have x. M is what? M is the value of m. I double click. I give 10 values, right? 10. M is 10. And x, here's the size is 1 by 10. Double array. I double click x. Okay. Then I can see all the values of this x. 0.6 something, 0.7 something, 0.9 something, blah blah blah. So all these numbers are point to some value between 0 and 1, right? Between 0 and 1. So these give us a value between between 0 and 1. So we have random value between 0 and 1. You think this is experiment, then its value will be value between 0 to 1. Then what is the probability? Now we can consider like this. Let me write down. Okay. Example 1. MATLAB function RAND. Then I run x equal to rand 1m, give us m values of x, right? X. The x is between 0 and 1. We have these. After we run this one, we get this one. Then what is the probability? Here actually, between 0 to 1 we have infinite value. So if you want to find every point, how many, what is the probability? That is a kind of things, too much numbers. But we can consider some event. Consider event, right? Event, we choose part of it. Okay, so here is s equal to, I write in this way, 0, 1. That means interval from 0 to 1. Okay, so this is sample space. Then consider event. Anyone you can choose. Like A, we consider This is x, right? X is a value, random value. I want the x between, now it's 0 to 1 is whole sample space. I think I consider x from 0 to 0.6. I consider this as A. Then what is the probability of A? Okay, we just use this one. We take account how many x in A. We try m times how many x in this event. So here, like here, this is x, right? This is x. We have 10 values. Then we take account how many x in these. Okay, how many x is in the interval between 0 to 0.6? Not here. This one, 1, 2, 3. So we have 3 now. So 10 out of 3, right? If we consider these, okay, we try A. We try 10, not 8. 10 samples. 10 samples with 3 or 4. Sorry, I forgot. Just take account again. 1, 2, 3. Okay, we have with 3 in A. So we say probability of A close to 10 out of 10. That is 0.3. Is this a good number? Approximate. You know, it's close to, but actually this is not really close. You only have 10 samples, too less. We can try more samples, which we repeat it more times, then we can have better approximate to the probability. Here I use 10, right? I can use like 100. And to find it, we use this. I use S, which is x larger than smaller than 0.6. Okay, I try 10 times again. So by this way we can try whether the program run better or works, whether it works. Okay, it's a F5. Then I have S. You see, S is 1 1 0 1 1 1 1 0 1 1. So that means, okay, we can also see what is x this time. These are the value of x, 0.05779. When we get this one, this number is smaller than 0.6. So here you see the code. The code is x smaller than 0.5. This is a logic operation, right? Remember, the different programming language might be different, but this one is same thing. This is logic operation. We will check whether the value x is smaller than 0.5. If x is smaller than 0.5, this one gives us 1. So s will equal to 1. If x is larger than 0.6, then this is fail. This is not true. This is fail. Then s will be 0. So here you see, we compare the both here, x, they are the value of x, and they are the result after you take the logic operation. So first two, I get 1 because these two values, they are really smaller than 0.6, and this is larger than 0.6, so it is a fail, it's 0. And then smaller than 0.6 again. So okay, I get S. Then some are 1, some are 0. Okay, we do a summation. This will give us the totally number A occurs. You got it? I do a summation, right? When we have 1, that means A happened. When we have 0, that means A didn't happen. Then you take account how many 1s. That gives us the number A happens. So we just do summation of S. We do summation, we can have the whole amount of A happens. Okay, so here if I go to the code here, I have as, then I just use I say k is the summation. This is also a building function of MATLAB, just do summation of all the elements of S, and then the probability or equal to k over m. Okay, let's run it. F5. I got 0.6. Now this time I got 0.6. If I run it again, it's a lecture. I can run the whole file here. I just put the file name here. I don't need the .m. Just this one. Lec01F. I type this name of the function. Return. Okay, I got 0.6. I do it again. Still 0.6. Every time I got 0.6. This is 0.5. Okay, 0.5 should be better. You see, every time you can have different value depending on the samples, because every sample is randomly. Now let's increase the whole amount. How many times we do the experiment? I say here m is 10, right? If I try like 1,000 times, what will happen? If I say wrong. Okay, 0.59. I run again, 0.57. Run again, 0.58. 0.604. 0.5860. You get it? So what will be the right probability? Actually here the event is between 0 to 6 and the whole sample space 0 to 1. If you compare these two, you can see this is S from 0 to 1, right? This is S, and A from 0.6. This is A. This is A. So you combine them together, you can see actually this is just 6%, 60%, right? Yeah, it should be 6. Now I have 1,000 samples. Then we have this one close to 0.58, right? We try more, and we have several. You see, 5.58, 0.603. I write it on the paper, on the notes. Okay, like this, right? You try different time. Every time you take 1,000 samples, you can have different. Every time you have some values. They're quite close to 0.6. 0.6. Actually, it should be 0.6. If we get even more samples, we try more experiment. Now it's 10,000, 1,000. If I use 10,000 examples, we take 10 samples, we repeat it 10,000 times. Then, okay, that's fine. After I run it, it's 0.58. Okay, I run it again. 58, 5960, 5960, 5960. Okay, you see, in this case, when we take 10,000 samples, the result, the approximate of the probability will be quite close to 0.6, right? 0.6. Okay, so we can claim. Actually, we can claim here probability of A should be 0.6. We can claim this. Alright. Yeah, we try 10,000 samples. Try after 10,000 samples, we can have this one. If you try more, you can even use larger number of the M for more samples. Alright. Okay. Now we try to work in a different way. We still consider this function ren, but we try to work like this. We try to find a set of event. Example 2. Example space, it is still from 0 to 1. X is just that random function. Okay? And we consider the event totally is 0 to 1, right? Event I separate as 5 pieces from 0 to 1/5. Here I use this way, and here's this way, 1/5 to 2/5, then 2/5 to 3/5, then 3/5 to 4/5, and then 4/5 to 5/5. That is 1. Now we consider events. We have 5 events. The difference is here. Like this one, I contain 0. This one I contain 1/5. This one I contain 2/5. But this side do not contain this one. Like this is a 2/5 smaller than and equal to that x, and x is smaller than 3/5. This is event like this. I use number like this is a B1, B2, B3, B4, B5. I have 5 symbols, 5 events, and we can try to find the probability of these 5 together. We use a function, MATLAB function. It's a histogram. Histogram. This function, this one, hist function. We use this function to find probability of this bi. I run from 1, 2, 3, 4 until 5. 5 events. We try to find the probability together. Okay, then we can work like this. Okay, x is still x. I take x, but I use a different way to calculate. I don't need this anymore. Okay, when I put these nodes, that means put this one. That means they are nodes. They will not be wrong. I still use s, but this time s will equal to. I have 5, right? I have 5. X run from 0 to 1. Now x times 5. It will run from 0 until 5. And I separate these into 5. I use what? I use floor. Floor is a function. It will give like this. Okay, let me write here. Let me explain something. This one is a histogram. Histogram. Yeah, things looks like. Yeah, it looks like this. And floor, see like this. Floor of 2.3 equal to 2. Floor of 0.5 equal to 0. Floor any number like a 4.621. This is just 4. So it is just this number go to here. This one go to here. Alright. Yeah. If like floor 5.0, this is 5. Right? This is 5. So we call this is the floor. And we also have cell. This is the function. 0 to the 3 will be 3. 0.5 should be 1. 0 for the 6 should be 5. And 0 for 5.0, okay, this is still 5. And we have this. Alright. Now we use this one. Now we go back to MATLAB. Here, I added the function. S times this, and x times 5, then I put a floor. So the result of S will be some integers. We can try take 10 samples and we can see what is S. Okay. F5, it run. Okay, now I have a different S. See what is S? You see, S will be 1, 4, 2, 2, 1, 1, 2, 4, 3, 2, 4. So this time, each number, the one, this is not 1, this is 4 here. Yeah, the first one is index. This is 4. So that means B4 happen, right? This is 2, that means B2 happen, right? When you have 2, that means x is 2 dot something. So this x is value between 2 to 3. And I multiply 5, right? Before I check the floor, before I use the floor, I times 5. So if you go back, that will be over 5. So that is a 3 over 5, right? 2 to 5, 3 to 5. So that is a B2. So here, when you check these numbers, this 4, 2, 2, 1, 1, 2, they are just the B. This is 1, that means B1. This is 4 means B4. This 3 means B3. Yeah, things like that. Okay, so now I have S. Then we can run the histogram. Histogram of S, and we have totally 5 values. I think this is correct. We just run it. F5. This one will give us a graph. Okay, give us a graph. Look like this. We have 10 samples, and 3 of them, their values is from 1 to 1.5. That means center is 1, right? And no value related with 2. Okay, I have 5 related with 3. 5 of them are 3, and 2 of them are 4. You got it? Yeah, so we have 5 numbers like this. Now we can also more better use this way. It's from 1 to 5. Okay, this way. 1 to 5. This is better. Yeah, this is good. 1 to 5. So we have 5 intervals. Each interval, 5 bars. Each bar, the center value here is 1. Right? This is 2. And we can also see what is S right now. What is S? S is here. 2, 3. Oh, I have 0. Oh, I use floor, so I will have 0 to 4. No. So I have to make some changes. I want 1 to 5, not 0 to 4. So this is the floor. That will be 0 to 4. 0 to 4 and plus 1. Plus 1, there will be 1 to 5. I need 1 to 5. Plus 1. Okay, this gives us 1 to 5. Let me run it. Okay, the graph will look like this. Its value from 1 to 5, and its value, you can see S is 2, 4, 3, 5, 5, 4, 4. Okay, you can compare the value here. You see, how many ones do we have? There's no ones, right? No one. How many 2? We have 1, 2, 3, 4. We have 4 2's. So you see, here's a 4. Here's a 4. Got it? And how many 3? If you look at histograph, this is just 1 3. And you check here, how many 3? You have 1 3. Yeah, just 1 3. And then you will have 3 4s. 3 4s. You see, this is 1, 2 3, 3 4s, right? And 5, we have 2 5s. Here's 2 5s. 2 5, 1 2. Yeah, this 2 5. Okay, so this is histograph. This is the values. Alright, now we try large numbers. Large numbers of the experiment. We repeated it like 10,000 times. 10,000 times. Then I run it again. Oh, looks like this. I have 10,000, and each number will occur about like 2,000. Totally 10,000. So you see, they are quite equal likely. They're quite almost same. So this is a as we said, as the MATLAB explained, you help. You type help of these rand. Then it will explain. So this is a uniformly distributed random numbers. You see, so the value were between 0 to 5, and each number will occur, equal likely. The probability is similar, right? So uniformly. This is the name. Later we will explain this in more details. Okay, now we understand. We use the rand function. If we separate 0 to 5 into 5 different pieces, and each piece with a probability, you check the probability of each piece happen, there will be almost 1/5. 1/5, right? The probability should be 1/5. If you this 2,000 divided by that 10,000, you will have probability. We can calculate it here. This is a graph. Let me give I use this again, but this time I do not draw a graph. I put this in a number, in a name, like that is S. I use this as another S. I have X, right? X is I use Y. X is a random value. X is the experiment, result of the experiment. And this S give us the index of the events, right? And we have 5 events, B1 to B5. And Y will be the actually Y will be the totally amount of X belong to each event. Right? Belong to each event. Let me write it. Okay, just like here. You try to run it, you will see what is Y. Okay, let me run it. Then I have a Y, right? After I run it, I have a Y. Then I double click on Y. You will see, okay, you have 1970 as 1, 1974 as 2, and then 1988 is 3. 3 means B3. 2042 as B4, and 2026 B5. Right. So how many times we get B1? This is the time, and so on. Then what is the probability? I just use all these numbers divided by that whole amount M. Okay, this is Y. Then the probability will equal to just Y over that M, capital M. Okay, I do not put this semicolon. Semicolon. I don't put it. Then it will display this value. Let me run 5. Go to the command window. You can see. Okay, our result is get this one. They are the probability of each event. And here we run how many samples? We have tried 10,000 samples. By 10,000 samples, we know each event, the property actually close to 0.2, right? You just think it's a 0.2. Okay, let me write. 10,000 samples. I have the probability of HBI is just 0.2. I run from 1, 2, 3, 4 until 5. Alright, so we have this one. Yeah. Okay, this is a second example. Third one we can consider, actually in MATLAB we have another function, random. DOM. Random, you see, random generate random numbers and from a named distribution. So distribution means the distribution of the probability. You have some value randomly, then which number will have how many probability. And here the name, the distribution, you can see the name can be, okay, all of these, they are the name of the distribution. So in MATLAB they provided this a lot, right? 1, 2, 3, 10, 1, 2, 3, 4, 5, 6, 7 here. Several tens, maybe 20s, different distributions. Then if you are interested, you can pick anyone. Then you can see, okay, some what is the sample space, what is the probability of some given event. You can try this. So here we can try, for example, I try some whatever, the first one, what is beta, right? We can try this beta. So we use this one, let me see, name, right, and M, and A is a parameter, and M and N, there will be the size of the random value. Okay, beta, I just use beta. So how many parameters for beta? Just copy this. I put it in here. Alright, we try another one. I put the command. So I put the command, that means they will not be wrong. Then I use this random. Okay, this is not this. Yeah, even not X. I do not use X. I use another X. I still use X. I prefer use X. Okay, X is random. We have to use lowercase letter. Then the name, I use name as bait. Then the parameter A, I don't know, I just put like 6. Does it work? And M and N, I use M is just M, N is 1. Okay. And M, we start from 10 numbers firstly. From 10 number, when it is works well, then we can increase M later. Okay, now F5. Okay, incorrect number of input. Oh, so this might be more numbers. So bait, I put 4. More parameter. Okay, it works. Alright, so bait needs 2 parameters. Bait is a kind of you think is a kind of experiment. This is experiment bait with parameter 6 and 4, and we create 10 samples. We repeat it 10 times. Then we have 10 numbers. And you can see the value is between something between 0 to 1, right? So most possibly this one S is kind of a sample space should be 0 to 1. Okay, so let me write here. Here's another example. Example 3. I use X is random bait 6 and 4 and M and 1. I use these, and S not so sure, but most possibly, right? It is between 0 to 1. 0 to 1. Oh, sorry. Right, between 0 to 1. And we can check where I still use B. Consider event B1, B2 to B5. They are this is from 0 to 0.2, then this is 0 to 2 to 0.4, and last one is from 0.0.8 to 1. Yeah, still use this one. I still use this one. Oh, sorry. The paper, the document. Yeah, here. The sample space most possibly is between 0 to 1, and we consider these 5 events. Each one is x between 0.1 to 0.2, 0.2 to 0.4. Every 0.2 as one event. Right. And this is a 0 to 1, and I separate the 5 pieces. Right. 0.2, 0.4. Here's a B1, B2, B3, B4, B5. Okay, then I separate them. I use it's something similar like this. So now I still use S. I times 5 and take the floor and plus 1. Then this will be S, and then we can see the histogram of S, and also put the value in a Y, and then find the probability. We can do the similar thing. Okay, this is 10 samples. Now it's 10 samples. Let's try whether it works. F5. Probability. Okay, this probability is 0.2, 0.2, 0.4, 0.2. 10 samples is not so correct, but this one is okay. This is a histograph, and we can try more. Now we try more. Am I correct? Let me see. Times 5 take floor plus 1. Yeah, so the S will be the number of the index. Let me see, what is S? S 4, 2, yeah. Some 2, some 4, some 3, and 5. Okay, now let's run more samples. Here's 10 sample, right? We can have 10,000 samples. Run it. F5. Oh, display. So okay, let me remove this X, right? Do not display. Okay, run it again. It's here. Okay, it's here. And the histograph looks like this. Maybe some values larger than 1. So the sample space might be larger than 1. Let me try more. Sorry, I'm not so sure, right? I think the sample space is from 0 to 1. Now what is sample space? Let's see. Maximal of x. We check this. From the maximal and the minimal, both. I want these two numbers. That's fine. 0.9, 0.1. Okay, it should be correct. After I run 10,000 samples, I have a little bit chance. I get the largest number will be 0.9, and the smallest will be 0.1. So okay, so it's between 0 to 1 is fine. Yeah, the sample space is between 0 to 1, and I use 5. I separate 0 to 1 into 5 pieces, five events. Actually, this is a partition, right? This is partition. 5 pieces. They form a partition, and each piece with a property looks like this. And if we give the histograph, looks like this one. And we can have more histograph, right? I separate it as 5 pieces. If we separate more, let me see. Here's 1 to 5. 1 to 5. If I do not use 1 to 5, okay. I just put here, like I put 20. I just put the number 20. Then the system, the MATLAB will separate the histograph in 20 pieces, 20 bars. Something wrong. Oh, I need to remove this. Okay. 20. Okay, the value just 0, 1, 1, 2, 3, 4, 5. Okay, it seems the number they are. Oh no, sorry. I change this to 20. This should be also changed to be 20. Okay, I use a J for this. J for how many events in those B's, in those event space, in those partitions, right? Partition. J equal to 20. Okay, Fi. Alright. Why this bar looks like this? Let me try again. Fi. Oh, some sample. I don't have some samples. Yeah, we can see if I give more samples. F5. Yeah, okay. Yeah, we have more samples. Then between 0 to well, this is 20 histograph. Oh, I have 20 pieces. I separated the whole space into 20 pieces. Here they display to be 20. Yeah, actually this should be from 0 to 1, right? 0 to 1, and then separated into 20 pieces. And each pieces, the probability of each pieces is close to the number shown here. Right? So it looks like this. Not the number here. It's divided by the whole amount, get the probability. And then I have the probabilities here. This is the probability, PR. I list all the probability values here. And of course we can also give the graph for the probability. For example, here I use another figure 2. That means another figure 2, and the plot, not plot, the stem of that PR. Okay, FI. Okay, I have another graph. Oh, we always have chance there's no value between in some interval. Anyway, so this is probability. Probability. Okay, this is a beta distribution with parameter 4 and 6 and 4. If I change something, for example here I choose like a 2, we can see what will happen. This is a different experiment, right? Same kind of experiment, but parameter is different. Then let me run it. Okay, it looks like this. Oh, the figure 1, figure 2. The first graph I need a figure 1. Then you will be lost. Here, histogram. This one. Figure 1. In figure 1, I draw the histograph. Then in figure 2, I draw the probability. Okay, so this looks like this. I change the parameter, then the waveform looks different, right? Okay, so this is a beta 2-3. Right? I change to 2-4, beta 2-4. This is beta 2-4. All right. Okay. Oh, the time is over. Sorry. Then I just want to say, if you are interested, you can try. Here, in the MATLAB, this function random. In this function random, here you can see they have different kind of distribution. That means you can think they are different random experiment to give different way to give the result. You can try different one with different parameter, but yes, there's a lot. You can pick 1 or 2 and try it, and to see some graph looks like this or this. You know, then you can have some sense about different kind of distributions of the probability. All right. Okay. All right. That's all for today. See you next time. Have a good weekend. Bye bye.